Yeah. Anyway, well, we have to go on, and let's get started. Last time we discussed the first type of unsupervised learning, which is clustering. When you're given a set of data points, and you learn how to separate them into different groups. Yeah, so a very discrete type of separation of the points. Yeah, so sometimes you say, well, that kind of separation might be too harsh. Yeah, what if I have a point, say, that's at a boundary between two clusters? Yeah, do you group it into this side or that side? Right, it's a bit tough. So a softer way to learn, a softer way of representing those data points is a distribution. Yeah, it's a continuous shape to represent those points. So more precisely, given a data set, again without labels, just m data points, and we assume that each one of them is drawn from a probability distribution. Okay, P of x here is a probability distribution. And we say this is IID, where IID stands for independent and identically distributed. Right? Independent and identically distributed. They all have the same distribution, P of x. Okay? In particular, P of x here, we use the probability density function. Of a random variable. In this case, well, very often we use a capital letter X to represent the random variable. Yeah, the small x is the value that the random variable takes. Yeah. So, in other words, we view these n different samples as just n samples drawn from a common distribution function, a common density, P of x. Yeah, they all have the same distribution. Okay. So, and then our goal would be to estimate this P of x. We don't know what P of x is. We're only given the data points, right? So, as an example, let's look at a case where d equals to 1, just one-dimensional. You have n points. Let's say the n points looks like this. A bunch of them here. Let's say, a bunch of them here. Yeah, like that. Okay? So you're given these points in one-dimensional space, and you're asked to estimate that density function for which we take these points. These are just the outcomes of that random variable. Yeah, you remember in probability course, what is a random variable, right? It's this quantity that can take different values depending on randomness, right? And these are the different values that it takes. Yeah, you have n different values for this random variable, and you want to estimate the density function for this random variable based on this value that it can take, right? So as you might imagine, when there are more values here, then you think that, well, the probability that the random variable is here is higher, right? Yeah. So density here will be higher, whereas here might be lower because the density of those points are not as high, right? This is pretty much the meaning of density, anyways, right? So you might imagine the density function might look like this, yeah, and something like that, right? That would be a reasonable guess for the density of the random variable x. Okay. Does it make sense so far? Yeah? And your job is to actually estimate this one, right? Because you don't have that density function, right? So your job as a learning job is to output a p hat of x, which is the estimate. Yeah, let's say, well, and estimate of p of x. Yeah. Just by looking at the sample points. Well, the application of this, we alluded to a little bit last time. Yeah, will be, say, anomaly detection, right? So suppose you want to know what is normal. Yeah? The training data that you're given represents the normal data points. Yeah, in general, it looks like this. So you generate this PDF, this density function, and then later when a new data point comes in, you ask, well, is this data point a common data point or abnormal data point or not. Depends on if the new data point falls around here, then say, well, yeah, most likely this is a normal data point. Okay, so I expect to see a data point here. Yeah, but if a data point appears over there, yeah, right, all the way at the tail, then you think, well, maybe this data point is not a normal one. It can be an abnormal data point, and this could be very useful. For example, in the computer network when you want to detect attackers. Yeah, you have your normal data traffic, Netflix and web serving or whatever, right? They all have a certain look, and then suddenly you receive this new data point, this new flow of traffic that's way out there at the tail end of a distribution. Then you know that one looks strange. You might want to pay attention to it. Just check it out. Yeah, make sure that it's not a real attacker, right? So that's a very important application of density estimation. Abnormality detection. Okay. So since we're talking about probability density functions, just so that everyone is on the same page, let's have a quick review of random variables and the distributions. Yeah, we have two kinds of random variables, right? We have discrete ones that takes discrete values, and these ones, let's say x is a uniform discrete random variable in the set, let's say 10 possible values. Yeah. For discrete random variables, it does not have a density function, right? Well, you can define it using delta functions, but it's not a real function. But usually we use probability mass function to represent a random variable like that, right? Probability mass function is simply just the probability that this random variable will take a certain value, right? So if it's a uniform random variable, the probability it takes any value is the same, yeah? And there are 10 of them, so this one will be equal to 1 over 10, but only if k is among the possible choices, right? It's only for k equal to 1, 2, 10, yeah? The probability x is equal to 11 will be 0, yeah? Okay. So that's a discrete random variable. For continuous random variables, let's say again it's a uniform random variable. It takes continuous values, obviously. So the value can be in a certain continuous interval, right? So interval, let's say between A and B, yeah, like that. And usually we don't. Well, it does not have a PMF really, because all of the probability mass will be 0, yeah. For continuous random variable, the probability is equal to any particular value is always 0, right? So we don't use PMF, rather we use PDF, the probability density function, yeah. And the general notation is f of x like that, and then small x inside, right? It is the probability density function of the random variable x, yeah. And it takes a certain value at this point of x, small x. What is this equal to? Anyone remembers? For uniform random variable, what is the PDF? Come on now. That's a prerequisite for this course, right? Yeah. Yeah, 1 over b minus a. Yeah. It has to be the same everywhere, so no matter what small x is, it's the same, it's flat everywhere, right? And then the area underneath the curve has to integrate to 1. Yeah, that's why the height here has to be 1 over b minus a, so that the area underneath the curve has to be 1. Yeah. So that's what it looks like. Outside of the range is 0. So therefore here we want to specify this is 1 over b minus a for x between a and b. Yeah. Outside is always 0. Okay. So let's look at another example of a continuous random variable. The PDF, an important one for the purpose of this course, is the Gaussian random variable. Yeah, one way to write this is a n, scripted n like that, which stands for normal. Gaussian random variable is also called normal random variables, right? So it's a mu and sigma squared. Yeah? Of course, mu is the mean value, sigma square is the variance, right? And the PDF of this guy looks like what? It's a Gaussian random variable. It's a very well known, so it should ring a bell at least, even if you do not remember the exact form, right? It's exponential to a square term, right? So the square turns out to be the x minus mu square, and then over 2 sigma square like this, yeah? And in terms of the picture, it is a upside down bell shape. Well, bell is always upside down. Anyway, just a bell shape, center at the mean value, right? And it roughly looks like this. Yeah. And the standard deviation is sigma, somewhat corresponds to the width of the bell, right? The wider is the bell, the larger sigma is. Yeah? The more uncertainty there is in this random variable, right? Okay. So that's just a quick review of single random variables and what is the PDF of a continuous random variable. Now we can go back to our original problem. We want to say, given data points, we want to estimate this P of x, this probability density function, from which we draw or we drew those samples. Yeah, a single PDF from which we drew all of these n samples, right? Yeah, they are all identical distributed samples, and we just have to recover the distribution. Yeah, that's our goal. So today we're going to talk about 3 different methods. Yeah, the first method is a naive one that you might have already seen or in fact used. Just the histogram method. You want to estimate the distribution of a random variable. You just take the samples and take the histogram. Yeah, it's a kind of a naive method. Histogram method. Yeah. Okay. So to take the histogram, what do we do? First of all, to take histogram, you have to define a certain bounded region, and then inside the bounded region, you count the number of points. Right? So suppose all data points in D, scripted D, fall inside a certain region, a bounded region. Let's see, denoted by a scripted X like this, okay? What do we do? Well, how do we do histogram? What is a histogram? You should have heard of the term histogram, right? Yeah, I think it's something that we learned in high school, right? Yeah, I'm sure you, at some point in time you did this in high school, right? Just say the histogram of the age of a population of people, right, in a city. Right? You group them into bins, right? Age of 0 to 10, 10 to 20, 20 to 30, 30 to 40, and so on. Count how many people are there, and just plot the bars. Those bars represent the number of people in those bins, right? That's the histogram. Yeah. So we're going to do the same thing here. Yeah. So you're going to divide this region into bins, right? Let's say divide this into uniform bins. Yeah, and in high dimensional space, in d-dimensional space, this is what we call a hypercube, right? And then you just count the numbers in those bins. Yeah. Well, before we go there, let's give them names. Yeah. Let's say we have k different bins. And then they are all equal size. about that. So let's draw a picture for the two-dimensional case. Suppose this is your x range, yeah. And well, I'm sorry, I should draw the points first. Maybe, yeah. You have these points. These are the points that you're given, right? And then you say, well, to estimate the distribution, I'm going to divide my x into bins, yeah, like this. Let's call this B1, B2, B3, B4, right? And then just count. Suppose you have Ni, yeah, be the number of points in Bi. Yeah. Then we're going to simply say that, well, in that case, we just guess or hypothesize that the probability that a data point will fall inside the bin will be just Ni over the total number, M, right? That's how you would find the probability. So we hypothesize that, first of all, the probability that this random variable for which we are trying to estimate the density function falls inside a bin, of course, should be equal to Ni over M, right? This part should make sense, right? You know, just based on our histogram, based on the data that we were given, that would be the best estimate for the probability, right? It's inside the bin, just how many of them already in the bin and divide by total number. Yeah. Second thing, well, because we have to actually find the density function, right? This probably is not a density yet. It's only just a rough idea about where the points are, yeah? So see discrete. To make a density, a smooth, continuous density, we have to make an assumption that inside each bin, the density is the same. It's a uniform density inside the bin. Okay? Usually this is fine if your bins are small enough, right? When the bins are small enough and everything looks flat, yeah? Imagine the density function. You divide them into different bins. If the bins are narrow enough, the function inside the bin appears flat. Yeah? Just a calculus notion, right? That's how we do calculus. Yeah? You divide into small bins and the function looks flat. So the second assumption or hypothesis is that the distribution of points in each bin is uniform. Okay, and if it's uniform, that would mean, in other words, the density of x, yeah, given that this point is in Bi, yeah, given that it's in Bi, where can it be? Well, that density of where it can be is simply uniform. Then what is the uniform PDF in this case for inside this bin? What should be the density then? How do we express this idea that the distribution is uniform? So this is given that the point is already inside the ice bin. Yeah, where can it be? Right? What is the density inside the bin? Where can it be? It's the same probability, right? Because we assume it's uniform. It's the same everywhere. So it's uniform inside the bin. Remember just the review that we did? How do we write the PDF, the density of a uniform random variable? Uniform random, that's what we did here, right? This is a uniform random variable. It's just 1 over the size of the region, right? So we already assumed that the size of the region is V, right? Our bin size is V, so therefore this is simply 1 over V. Yeah, right? Okay, 1 over V. And of course this only for x that's inside Bi. Yeah? Okay. Therefore, if we hypothesize in this way, then what is the overall estimation for the density function? So over here, we already have the conditional density function, right? Conditional on the event that the random variable is inside BI. But then we say overall density. How do we find that? There's a theorem for us to do this, right? What is that theorem? You already know the density for each case. The sum of the cases, yeah, that's called the total probability theorem, right? I hope they certainly should ring a bell, right? The total probability theorem. Yeah, it's one of the most important theorems that we know from our probability course. So we sum up all of the possible cases, j equal to 1 to k. But so each one of them, we sum up this conditional density. Yeah. But we don't just sum up the conditional density, right? We have to weight this by the probability that the random variable is in that bj. So that's the probability of the case itself. Hold on. Let me try to reset the pen a bit. Otherwise, I'll change the battery. So this is a total probability theorem, and we can write it out since we already know that this one is 1 over v, but this one is 1 over v only if you are inside that BI, yeah? Only if it's inside the BI. So we have to write the indicator function here for this being in BI like that to be precise, yeah? Because now we involve the other possible cases, right? Yeah? So this is one is the indicator function, right? Yeah. If it's inside, then it's 1 over v, but if it's outside, it's 0. Yeah. And then what is the probability of x is in B? Well, going back to our first hypothesis, right? X is in B is ni over n. So this is ni over n, like that. Okay. And because of the sum over an indicator function, you can actually cancel them out in some sense. Yeah. This one only active when I, did I say j here? I'm sorry about that. I should have I, yeah? I goes from 1 to k, not j. Sorry about this. This is I. So this essentially is just break them down into different cases. Right? This sum is not really a sum. It just says that it's 1 over v n1 divided by n if x is in B1, yeah, and so on, yeah. You just break this down into different the individual cases. Like that. Okay, that's what the line above means. Yeah. In fact, if you just look at this makes a lot of sense, right? You don't need the intermediate steps, really. Yeah? If you just think about how I can find the density function using this histogram method, yeah? I just assume that everything is flat inside each region, right? And then the probability of each region is simply these numbers, the ratio of those numbers. Okay? You don't really need to go through the middle steps. You know, adding the middle steps just made this idea more rigorous. Yeah, just mathematically derive it and so on. So let's look at a quick numerical example. The example itself is very simple, but we just want to get to one point that's slightly more interesting. Yeah? Suppose we have one-dimensional space, and the region of interest is between 0 and 3. Yeah? So let's say just one x like that. Let's say 1, 2, 3. Let's say we have 2 points here, a point there, and then maybe 2 points here, like this. 5 points that we're given in our data set, okay? In your notes, make sure that when you drew this point in the middle, make it closer to 2 rather than to 1, okay? Because for the next step, it makes a difference. So given these 5 points, we have to estimate the density, yeah? And using the histogram method, we just say, well, let's say, suppose we use, let's say if V is 1, okay? We use bin size of 1, yeah? Then what happens? That means, well, this would be a bin, this would be a bin, with 3 bins like this, right? What do the lines look like? Oh, okay, I give up. Let me change the battery. So how we, just look at the formula above, right? How do we do this? So in the first bin, there's another bin here. What should be the height of this? Well, we know the inside the bin is flat, right? Should be like this. But what is the height? Well, just by our formula is 1 over V, 1 over 1, times the number of points that we have inside the bin, which is 2, over the total number of bins, right? That's 2 over 5. Therefore, this height is 5 over 2. Yeah? And then in this one, well, it's again 1 over 1, but then we have only 1 point out of 5, yeah? So this is 1 over 5, yeah? And then in this bin, it's again 1 over 1, 2 points out of 5, so 2 over 5, yeah? Simple as that. And altogether, therefore, this is our density function, our estimated density function, given this data set of 5 points, yeah? Okay? Easy enough, right? Pretty simple, just a simple histogram approach. Now, what if now we try V equals to 1.5? What does it look like? We still have 1, 2, 3 here, same points. Yeah. But now, because it's 1.5, the boundary is here. This is B1, B2. We won't have 2 bins, right? And the first bin, in the first bin, we have 1 over 1.5 times, we have 2 points over 5, right? So this is 4 over 15. Yeah, that's the first bin. In the second bin, we have 3 points out of 5, so it'll be higher. Yeah. So 1 over V is still 1 over 1.5 times 3 over 5. Yeah, that turns out to be 2 over 5, like that. Yeah. So if you use a different bin size, you get this PDF. Yeah. Okay. Both of them are valid PDFs out of this same training data set. Yeah. Just depending on what granularity we want to use for the histogram. Yeah. Okay. Then a natural question is, well, what kind of granularity should we use? Okay, right? Observing these 2 pictures, do you see the difference between these 2? You have smaller beans versus wider beans. Right? Smaller beans will be more jagged, yeah? More up and down. Yeah? Bigger beans will give you a smoother PDF. Okay? But there's no definitive answer to say which one is better than the other, right? Yeah? It depends on what you want. So smaller beans, you get more granularity, but then you might be fitting those points too well, yeah? And we have a name for that, right? It's called overfitting. Yeah? So let's say if you use a smaller beans, then you have a more granularity. but then also more discontinuity. Yeah, it's overfitting. Okay. And overall, this kind of histogram approach will give you PDFs that are kind of discontinuous. Yeah, it has this boundary at the bin level. Okay, so even though it works and it's very simple to compute, it's not the best method to use. Okay? The next method try to address this issue. Yeah, and it's called a Parsons window estimation. Parsons is someone's name. Yeah? And we're going to use what's called the Gaussian kernels. The method was known still a long time ago, yeah, 1960s. The following is the idea. Yeah. Oops. Suppose, yeah, again, you're given some points. Where do I want the points? Here, another one there. Let's say 2 over here, like this. Okay? Yeah. So again, we want to estimate the density function that generates these sample points. Okay. The idea of Parsons is to assign each of these points a Gaussian curve, a Gaussian PDF, okay, what's called a Gaussian kernel. Okay. And then we sum them all up. Okay. So what does it do for us? Why does it help? So if I have a, let's say, Gaussian here, another Gaussian for that point. Yeah. So every point has the same Gaussian shape, okay? Everyone like that. And then the other one, let's say here. Okay, roughly like this. Okay, these are the same, all of the same Gaussian shapes. Okay? And then we're going to add up all of the Gaussians together. Let's see what happens if you add them up. So this one, well, on that side, there's nothing much to add, right? So it's roughly the same. But then here, because you're adding 2 of them together, you kind of get this kind of, well, a bit smooth transition, like that over here. Yeah. And then, but when you get to this side, because these 2 Gaussian shapes are overlapping a lot, yeah? So when you add them together, the sum is a lot higher. In fact, it's here, I think. So draw something like, well, it might look something like this, yeah? Okay. So you see, naturally, where you have more points, the resultant PDF is higher, right? When you sum them up like that, yeah, because of the overlapping. Okay. Now, of course, you still have to normalize so that the area underneath is still 1. Yeah. So instead of adding up, you actually take the average. But that's a minor issue. Yeah. The whole idea is that what you want is that when there are more points, you have a higher PDF, and that's exactly fitting our intuition. Yeah. Okay. So this is the sum. So this is the Parsons window estimation method, and that's the basic idea. And let's fill in the mathematical details. So we have to define this, each one of these Gaussian shape. Yeah? So it's called kernel. So phi of z is, let's say, use the standard Gaussian PDF. The standard Gaussian PDF is simply one that has 0 mean and unit variance, right? So this is the standard Gaussian PDF, probability density function. and it's also called the kernel in the Parsons window or Parsons kernel estimate method. Parsons kernel or Parsons Gaussian kernel estimation method. By the way, the coefficient in front here is a bit different from the one that's used in the textbook. The one here is the standard Gaussian, so that this one itself, when you integrate, it's equal to 1. Yeah? The textbook's version uses a slightly different normalization constant, but at the end it's the same. So if that's the kernel we are going to use, then our estimation would be what? You basically have these shifted versions of these Gaussian bumps adding together, right? For 1D, it's a simple. You have to shift and then add, shift and add. But now actually we have to do this for multi-dimensions, high dimension, d-dimensional data, right? So what we do is to just look at the norms between those d-dimensional vectors. Okay? Instead of simply shifting in one dimension, we look at the norm. So this one is a sum, let's say I equals to 1 to k, well, n of them, yeah? We have n points. Each one of them is a Gaussian like that, except that now we use x minus xn, which is location of that point. And then we further scaled up by a value r. Okay? Where r here is called the kernel width. Okay? So if you look at this carefully, so compared with the original phi, this is a mean shifted version, a shifted and then a scaled version of the phi, right? So shifted and scaled version of the Gaussian curve. Yeah? So this one involves shifting and scaling. Yeah? Does anyone see that? Yeah? So in fact, this r, the scaling of the r, the larger r is, this phi is fatter. Okay? Yes?
What is the double of r?
That's the norm of a vector. Okay, the L2 norm, yeah, just the square root of the sum of the squares. We have used this quite a lot, right? With the earlier work in supervised learning, we use this norm notation. Say again? What do you mean by taking the Gaussian vector? Well, this phi is a function of a single variable z, right? So we have to convert it to a single variable. Yeah, so we just take the norm. Okay? Yeah. So again, we shift the Gaussian to the location of the point, and then we also scale this Gaussian shape. We can choose to use a narrower Gaussian or a factor Gaussian, yeah, and it's controlled by this r. Right? So this phi is also called the this phi is also called the Gaussian radar basis function. Because now in high dimensional space, all that we care about is the distance between the points. We use this term quite a lot, the RBF of x. Yeah? X is a high dimensional vector, right? Okay. So here, all that we care about is the distance. So you can see around this xn, this point of xn, you just draw a circle. They're all the same distance. We count the same. Doesn't matter. Yeah. They all have the same impact. So that's why it's the radar basis function. Yeah. The c here obviously is the normalizing constant, right? C is a normalizing we have to normalize this PDF so that the area underneath the curve, the area under the curve is 1. Yeah? So the integration of the curve is 1, yeah, so that the integration of p hat of x, d of x equal to 1. Yeah? This, again, this high dimensional, d-dimensional integration. And in fact, c is equal to, there's a formula for that. You don't have to derive it, you don't even have to remember this formula, but just know that there is a normalizing constant like this. It's r to the d's power like that. Okay. What is underneath here is essentially the volume of a d-dimensional ball in space. Yeah. If you wonder what is the how do you find the volume of a ball of d dimensions? Yeah. That's the formula to use. Everyone doing okay so far? Any questions? Yes? Say again? Yeah, d is the dimension of x. Yeah. So again, it's just easier to understand this if you just imagine one dimension, right? In one dimension, the norm becomes simply the distance between the points. Yeah, you're just shifting exactly what we do there. That's one dimension. But you have to think about in high dimensions, what do we do in 2 dimensions, let's say. Yeah, in 2 dimensions, you just look at those 2-dimensional Gaussian bumps, right? You have to shift these different bumps to different locations by the distance. Yeah, this x minus xn norm, it simply tells you that's the distance that you have to shift. Yeah, and then you still have to bump. You add those bumps together. Any questions? Now, this R over here is the kernel width. So we said we have a choice on the kernel width. Yeah? How should we choose the kernel width? What is the impact of a wider kernel or a narrower kernel? So first of all, if R is small, is everyone convinced that this Gaussian shape would be narrower? This R pretty much serves the purpose of a sigma, right? The standard deviation or the sigma squared variance. Yeah? It serves that purpose, so this is R. Okay? So what happens when I use a smaller R versus a bigger R? Yeah? So let's say we have the case of a small R first. Yeah? Then x. Let's say we have just 3 points, yeah? A narrow one, let's say, is this narrow? It is a design choice, right? So we can choose this R like this, or we can choose a larger R. For the same 3 points, yeah. So an R that's very flat like this, yeah. So that's a large R, right? You have 3 bumps together, and then we're supposed to add them up, yeah. So what does it look like when we add them up? Well, for the left-hand side, they don't overlap too much, right? When you add them up, you still get almost like the individual Gaussian bumps individually, not much of a change. Yeah, maybe here change a little bit, okay, like this. Here change maybe change a bit more, yeah, but still, it tracks those points pretty closely, right? Yeah. Each point will give you a bump like that, and then it looks like this. When you have large R, then these bumps, these kernels, they overlap a lot, right? Yeah? And if you add them up, what does it look like? Well, let me see. Pretty much look like this, right? If you can imagine adding them up, will look like something like this. Yeah. So this gives you some hints about what we should do, maybe, right? What happens when we use should we use a larger R or smaller R? What are the relative advantages and disadvantages? Here, every point gives you a bump, right? So at the end, your PDF looks pretty jagged, yeah? Here, it's pretty flat. The PDF does not give you a lot of information about which part of the line is more densely populated. Yeah? This one gives you a lot of information, but then they fit to each data point very well, maybe too well. Yeah? So again, this one would be, what's the term for it? Overfitting, yeah, to your data. And this one might be underfitting because you're not generating much information out of your data. Yeah? So if you use too small an R, then you get overfitting. If you use too large an R, you get overfitting, underfitting. So this I is underfitting. Therefore, in general, you want to pick an R that's in between, yeah, give you enough information without overfitting. And in general, we can choose that by validation. Yeah. By the way, I did not mention this last time in this section. For k-means, how do you choose k? Okay. Turns out for k-means, to choose that k, there's no way even validation does not help. Because for k-means, the E in goes down as k increases. It never goes up. Okay. Even E out goes down. It does not go up. Yeah. So in k-means, there's no way to choose optimal k using validation, as opposed to here. For density estimation, you can actually use validation to choose R. Okay? No, so this is a good thing about the Parson window estimation. Yeah, it kind of, by just using this very simple method of summing things up, it kind of automatically gives you the density, which part is more popular than the other parts in the space. Yeah, because when there are more points, then you have more things to add, right? But there's a problem with this. Yes.
What would E out or E in? What would E out be in?
In k-means?
Yeah, like what does it mean though? Because it's just like a grouping of the vector space.
Yeah.
Like,
Since we have some time here.
like
Yeah. If this is the k, yeah, for k-means now, k-means. E in, you agree, right? It goes all the way up down to 0 when k is to n. When you have n clusters, the same as just every point is its own cluster. And the distance between the point and itself is 0, yeah? So E in here is always 0. So therefore, there's no way to use validation on E in, yeah, to choose an optimal k using E in. The hope is, well, what if we're looking E out, so some kind of validation data set, right? Would it go up or not at the end, yeah? Like in our other validation in supervised learning. But turns out that's not true in k-means. Think about it. What is testing? In testing, you form the clusters, and then you have a new point come in and ask, where does it belong to? And then you check the distance. That distance is the approximation error, right? So the more points you have originally, you find a closer point to you. You find a cluster that's closer to you, right? The more cluster you have, it's easier for you to find a closer cluster. So therefore, E out also goes down as k increases for k-means. So does not help you to use validation. Yeah, in validation, you still see that the E out decreases. The bigger k is, the better. Yeah. So therefore, what would be the optimal k to use? You have to go to use some other measurement to choose the best k. For example, you can say that, well, to build this system, every cluster that I have costs me something. there's a certain cost to use a cluster. So I don't want to have too many clusters. Yeah? And then you say, okay, I use a moderate number, 10 or 100 instead of infinite or to n. Yeah? So that's one thing with k-means. You cannot choose the optimal k using k-means. Okay? But for Parsons, you could. Yeah? You can just use validation to choose the R. But there are still problems with the Parsons method. Any suggestions? There are actually two problems. What could be a problem? This method, you have to sum up all these things, right? Look at this calculation. Sum up all n points. Your n can be huge in the big data problem, yeah? Your n can be millions, billions, yeah? But then you have to sum up all of them. The computation is enormous. So too many data points in general. Yeah? But there's a second issue. Okay? You notice that more subtle. Issue is that we only have a single R for every data point. And also for every dimension, right? With this d-dimensional data, we only have a single R for all of this, right? So this is too restricted. Some dimensions could be very different from other dimensions. Remember, we talk about this, right? In the person's attribute, could be the salary amount or number of children. Yeah? These are hugely different dimensions. Why do we only use a single R for that Gaussian shape, right? We should scale them differently, right? So that's another problem with Parsons window method. Yeah? Same R for all dimensions. Okay? All dimensions. And to address these two issues, we're going to introduce a new model called the Gaussian mixture model. And we'll take a break and come back to discuss that. Yeah? I see everyone looks a bit tired, much more so tired than normal. Under a lot of stress with exams, I'm sure, yeah. I know, yeah. Okay, let's resume. So we have seen the Parson window estimation. We've seen there are advantages of that method. Also, we saw there's an issue. There are issues. One is that you have to sum up every single point. For every single point, and there are too many Gaussian curves to sum up. And the second issue is that you have the same scaling, the R scaling, for all dimensions, which does not seem to be reasonable, right? And the Gaussian mixture model addresses both of the problems. Yeah? So the motivation for it is really, in a way, is in comparison with that Parson method. Yeah? So we have this one-dimensional example. We have a bunch of points here. Let's say, yeah, like this. Let's say like that. 10 points, right? And you want to estimate the density out of these 10 points. Parson's method, then you have to sum up 10 different Gaussian curves. Yeah. But if you look at this, with our very well-trained brain, we begin to see that, wow, those points are bunched up into 3 different clusters, right? And therefore, well, maybe I only need 3 different Gaussian curves. Yeah. But of course, those 3 Gaussian curves will have different characteristics. They will have different shapes. Yeah. So we might have a Gaussian curve here. That's a bit bigger because we have more points there. Yeah. I can have another Gaussian curve here, another Gaussian curve there. Yeah. So maybe I say, well, it suffices to use 3 different curves, and that's good enough. Yeah? One for each cluster. It suffices to use only, let's say, k Gaussian kernels or distributions. One for each cluster. And then you can, well, within each cluster, you can adjust the scaling. Yeah? Now, before we go there, since the Gaussian random variable is so important for what we do, let's have a bit of a review. Let's slow down a bit, especially since everyone is a bit tired and stressed out. So, as a reminder, what are Gaussian random variables? And we're going to go to 1 dimension, 2 dimensions, and then, in general, high-dimensional Gaussian random variables. Okay? D equals to 1. I hope this is a simple one. Everyone should know. What is the PDF of a Gaussian? Well, we did a bit of a review just now already. Random variable, let's call it x, with mean, mu, and variance, let's say sigma squared. Yeah. So we're going to write this PDF. Of course, it has this form, right? But we're going to, because we are explicitly only using Gaussian PDFs, we're going to use this notation for the Gaussian PDF, which is n of x, semicolon, right? Semicolon here, and then mu, and then sigma squared, like this. Okay? And this one, of course, by definition, has this form, the form that we should be very familiar with by now, even if you might not remember the exact form, it should look very familiar to you. Yeah? That's the single Gaussian random variable, the PDF. Yeah? As the n, again, stands for the normal random variable. It's called normal random variable because the Gaussian random variable shows up so often. Yeah? It shows up everywhere. That's why it's the kind of, in some sense, kind of anything that's normal would be Gaussian. And mu is an expected value, right? So it's the expected value of x. Yeah? And sigma square is the expected value of x minus mu squared, right? That's the variance, definition of variance. And we already drew this picture before. Yeah? It looks like this. Yeah? Center at mu with the width represented by sigma. Yeah? That's simple. equal to 2, now we're talking about the PDF of two jointly Gaussian random variables. Yeah? Jointly, this is an important term. PDF of two jointly Gaussian random variables, x1 and x2. Yeah? And well, each one of them have to have their own mean values, right? The means is mu1, mu2, variances, sigma 1 square and sigma 2 square. And we have one more thing, right? When you have two random variables, we have to talk about their correlation. Yeah? So we describe the correlation between these two random variables by their correlation coefficient. Right? The correlation coefficient, rho. Yeah? And rho, the correlation coefficient, is defined as the normalized version of the covariance. A bit of a strange thing, right? We normalize covariance to get the correlation coefficient, but that's the terminology that we have used, and that's what we have to stick to. So the covariance between these two random variables, of course, looks like this, right? The expected value of the mean shifted versions of them, or the product of them, yeah? And then this is normalized by the product of their standard deviations. Yeah? That's the correlation coefficient. I hope all this rings a bell, right? This is something, if you take EC 302, then this is towards the end of the semester, right? Then you learn about multiple random variables, and you get stuff like this. And then for two random variables, we have a joint PDF between them. Yeah? Joint PDF between these two random variables, fx1, x2. Yeah? Here, we're going to use this notation of n of this vector x1, x2, semicolon again, right? This is the input. And then the parameters will be mu1, mu2, sigma 1 square, sigma 2 square, and then rho. Yeah? Okay. This describes the joint PDF. Now, it has a very long form. You probably should have seen this in your EC 302 or equivalent class, right? Looks like this. Pretty messy looking, but then there's a certain pattern to it. 2 pi times sigma 1, sigma 2, square root of 1 minus rho square. And then you have this big E, yeah? E to the minus 1 over 2 times 1 minus rho square. You don't have to remember this formula, by the way. I'm just writing it down just to show you how messy it can be for even d equal to 2, right? What happens when d is larger? Yeah. So this is x1 minus mu1, mean shifted version of x1, yeah, square, minus 2 rho, and then x1 minus mu1 times x2 minus mu2, divided by sigma 1, sigma 2, and then plus the x2 side, x2 minus mu2, divided by sigma 2 square, like that. Okay? So that's the formula, the joint PDF between two jointly Gaussian random variables. What does this one look like? Well, it's just a kind of a two-dimensional, well, I'm not going to draw it, a two-dimensional bell shape, right? It's a, so if I have this x1 here, x2 dimension here, just imagine this being the two-dimensional plane, right? Then the PDF, of course, it will be a three-dimensional surface that looks like a bell shape. That looks like this, right? To indicate that there's 3 dimensions, maybe we can draw things like this, yeah? And then, well, maybe there's a, like that, yeah? You can imagine that this rim like this circle here when it's projected down to the two-dimensional surface, you will see just a oval shape, yeah? Doesn't have to be a circle, right? Because this bell shape doesn't have to be round, yeah? Could be a squashed bell shape, and the major axis of this squash bell shape doesn't have to be flat, yeah? Can be at an angle, with the x-axis, right? Different depending on the correlation coefficient between the two random variables. Okay, you should have all seen this in your probability course, right? At least rings a bell. Yeah, seen it. Even either you took a 286 or 302, or you should have seen it, right? It's a bell shape, a bump like this. So now, what about general case? T is greater than or equal to 1. 2, not 1. Well, actually, this is 1. This is 1, yeah, because this formula still applies to 2 as well, yeah. T is greater than or equal to 1, yeah. But of course, we're really interested in high-dimensional data, yeah. What happens? So you can imagine, when you go to high dimension, it will be much messier than this, right? Yeah. So, but fortunately, we can write all of this in the matrix vector form, which turns out to be quite clean, yeah, reasonably clean. Okay. So now we have D. D jointly Gaussian random variables. Let's call them x1, x2 to xd, right? D of them. And each one of them, of course, has their own mean values, the expected values. Mu1 to mu k, and mu d, and a covariance matrix now between every two. Well, the covariance matrix contains the covariances between any two random variables. Yeah? Let's call this a big sigma, it's capital sigma. Okay? Where sigma is defined as the collection of all of the pairwise covariances between the random variables. Yeah? So it's going to be the covariance between x1 and x1 itself, the first term, and then the covariance between x1 and x2, and covariance between x1 and xd. Yeah? And then all the way vertically you have until covariance xd, x1, covariance between xd and x2, covariance between xd and xd itself. Yeah? Like that. Okay? So it's a big covariance matrix. Yeah? That's our sigma. Okay? Well, of course, covariance, as we mentioned, covariance between any two random variables, that this you certainly know, right? By definition, it's just the expected value of the product of their mean shifted versions. So times xj minus mu j, like this, right? That's the covariance between two random variables. Have you all seen the covariance matrix before or no? It depends on where the professors go to at the end of the EC 302. Yeah, sometimes they are able to talk about more than two random variables, sometimes they are not. So anyway, this means if you look at this big matrix like that, and the definition of covariance, you recognize after staring at it for a while, this big matrix sigma can be written in a vector product form like this. Expected value of x, the vector, minus mu, the vector, multiplying x minus mu, transpose, like that. Okay? So here this is a column vector, yeah? And this is a row vector. A column vector multiplying a row vector, you get a matrix. Yeah? And then take the expected values. That's exactly the big sigma. Okay? So reasonably clean at the end if you can cut through those linear algebra representation of things. Yeah? The matrices and vectors. Now, turns out that when you have this big sigma, then you can write the joint PDF of this D random variables. So put them all together in a big vector like this, right? So we use the notation of n x semicolon, the mean, and then the covariance matrix like this. Okay. This one turns out to be equal to 2 pi raised to d over 2 power, and then the magnitude of sigma square root e minus half x minus mu transpose times sigma inverse and then x minus mu, like that. Okay, where this magnitude of sigma is the magnitude of the determinant of sigma. Yeah? That's what we mean by the magnitude of a matrix. Oops, what happened? Magnitude of the determinant of big sigma. Okay. So you can see here is a reasonably clean form for the jointly Gaussian PDF among the D random variables. Okay? And those of you who are really curious, you can look at this formula and set d equal to 2. Okay? For d equal to 2, this formula will give you back the one that we have above, yeah, for the case of 2 random variables, that messy looking form. Okay? But it turns out that even if you have a larger d value, the Gaussian PDF is not that messy, turns out. Yeah? It's, as long as you write things in matrices and vectors. Okay? It's very clean. And then also an important thing to note is that this PDF is completely determined by the vector of mean values and the matrix of covariances, right? So this mean vector and the covariance matrix completely determine the distribution of these Gaussian random variables. Yeah? And this is one reason why we like to work with Gaussian random variables. Yeah? They are completely determined by the first order and second order statistics. Yeah? The first order statistic being the mean, second order statistic being the covariances. Okay? It's completely determined by these two things. And this decides the bump. Yeah? For example, if you look at a two-dimensional case, yeah? This bump, right, the shape of this bump, the orientation, the width, completely determined by the first and second order statistics, yeah, the mean values and the covariances. Yeah? Yes? Here? Yeah. Okay, so with this quick review on the Gaussian random variables, now we can go back to the GMM, our Gaussian mixture model. And let's talk about how we can use it to generate data, yeah, for data generation. Yeah. So here, this is our model, right? This is our hypothesis. We are just saying, we're hypothesizing that the data that we're given follows this model. Yeah? Just like in linear classification, we're hypothesizing that those points can be divided into two sides by a linear line. Yeah? It's the same idea. So here we just say we hypothesize. This is a hypothesis. Okay? We're going to talk about how to use this hypothesis and to learn later. Right? So we use the same Gaussian mixture model to generate each one of our data points. So for each x that's in our data set, we do the same way. Yeah, of course, this x has to be a d-dimensional data point. Right? So suppose we basically saying that we don't use the Parson window. Now we say that, well, maybe there are k clusters that we can use. Yeah? So each one corresponds to one of the Gaussian distributions, right? So therefore, we only need to consider k different Gaussian distributions instead of n of them, as in the Parsons window case. Yeah. Suppose now we have k Gaussian PDFs. Then this, each one of them is defined by the mean value, right? And the covariance matrix. So it's mu1, to mu k, with k of them. And then we have a covariance, which is sigma 1 to sigma k. Yeah? Okay. And each one of them, instead of keep saying Gaussian PDF or Gaussian distribution, we just call them bumps. Very technical term, right? Yeah, but that's what we use. Just as in this shape, yeah, basically in this shape, the two-dimensional shape, yeah, it's a bump, right? Okay. So that's the term we're going to use. So how do we generate data points given this k Gaussian PDFs? Well, we just randomly pick one of these Gaussian PDFs, randomly pick one of these bumps, and say, okay, I'm going to generate my data point based on that Gaussian PDF. Simple as that. Once you pick that Gaussian PDF, you just use it to generate one value, yeah, the x. So that's how we do it. So first, we're going to pick a bump. Let's say j, yeah, that's out of our k possible bumps. But we say, well, how do we pick? Well, we're going to pick according to a certain probability distribution. Yeah? With certain probability, we pick one over the other. W1 to WK. Okay, here W, they are probability values. Okay, so in other words, we want Wi to be non-negative, and also we want the sum from 1 to k to be equal to 1, right? Because the probability has to sum to 1, right? Yeah. This is with certain probability, you pick one of them, and then you generate the data point based on that picked bump. Generate x according to the probability density function of the Gaussian. So of course this px, given j, right? Given it's a j's bump, then we know that it's Gaussian, right? Given it's a j's bump, it's Gaussian. It's, of course, it's Gaussian with the parameter mu j and sigma j, right? Okay. And if you want, you can just write out what we have. It's the same formula that we have before. This is 2 pi d over 2 d, half of the magnitude of epsilon, half x minus mu transpose. This is j now, yeah? J, don't forget. X minus mu j, right? Yeah. That's all. That's the Gaussian mixture model. Now, once we follow these two steps, what is the resultant PDF? Yeah. So hence, the overall probability density function for our data points is what? Under our hypothesis, under this GMM model, what is it? What theorem we use again? Yeah, we do total probability again, right? This is the conditional density. To find the marginal density, we use total probability again. So there are all these different cases. Yeah, j can go from 1 to k. And then Wj is the probability that you pick J. And therefore, once you pick J, you have this conditional PDF, like that, right? So therefore, this simply equal to J equal to 1 to K, Wj multiplying the Gaussian PDF, yeah? Mu J. Yeah, just be a bit slightly different, cautious is that this is a semicolon, right? My handwriting is not the best, I guess. Semicolon. This is J. Yeah, these are two different things, right? This semicolon. We always put a semicolon to separate those two sides, right? The x and the parameters. Okay. So I'm running out of space there, so I have to, unfortunately, I have to scroll up a bit. Look at a quick example. When k equals to 3, let's say, yeah, we have 3 bumps. Okay. Then we have 3 different, I just want to draw a picture to represent this GMM model in this case. We have 3 different distributions. It can be n of x. This is mu1, sigma 1. This is n of x mu 2, sigma 2, another one, n of x mu 3, sigma 3. These are 3 different Gaussian bumps at different locations. And then for each one of these guys, each index n, because we want to generate n data points for this D, right, for the data set. So we're just going to randomly pick one of these bumps, yeah? So one way to represent this is a kind of a switch, yeah? This is just a random switch. And you can maybe write W1, W2, W3 to represent the probability of this switch, yeah? Switch to all 3 of them. And then you pick one of them, path to go. Yeah, you just pick one path. Whatever path you get, you can generate xn, right? So you get the xn as output. Okay. And at the end, if you do this, what does it look like? Say d equals to 2. Again, yeah, this just make it easy to draw. Well, we have 3 different types of Gaussian bumps, right? Maybe one here, one there. I'm not drawing the 3-dimensional thing. I'm only drawing the contour map projected onto the 2-dimensional space, right? Is this okay? Understand what I mean, right? These 3 different things they represent 3 different Gaussian bumps that goes out of the board, like out of the page. Yeah, they're just different shapes of Gaussian bumps at different locations as well. Yeah. So you just pick one at random with probably W, and then say, okay, then I use that distribution to generate point. Maybe a point is here, yeah, and then for n equal to 2, you generate another point. The second point, well, maybe I don't know, it's there, right? Another point here, you know, at random, yeah, just anywhere, you know, based on these Gaussian bumps, yeah. So after a while, you know, you can just keep generating this, picking a bump and then generate a point. You get something that looks like this, right? Yeah. And that's the output of a Gaussian mixture model. Yeah. Okay. And you can see this naturally form clusters, yeah, because the points tend to aggregate around the mean value of that Gaussian bump, right? So you get some clusters. Okay. Yes. We are just hypothesizing how the data are generated. This is hypothesis. Yeah, we're just saying that the D data set that we're given is generated in this way. Yeah? But now we naturally lead to the question of what can we learn from this? Yeah? How do we estimate the right parameters, the mu and the sigmas? Okay? So That's the next thing, the learning problem. Given D, again, there are endpoints. And K, let's say we also know the number of bumps that we want. We want to find a GMM, a Gaussian mixture model, that is the best fit for this D. Yeah? To describe the GMM, of course, we have to collect all of the parameters together. So we're going to use this big omega to represent the entire set of parameters. So you have W, yeah, Wj, right? There's a mu j, sigma j, and k of them. Right? J can go from 1 to k, right? Yeah. So these are all of the parameters that we need to find, right, in order to pin down this particular GMM. Yeah, a lot of things to learn. Okay, and we want to find this. That is the best fit. The best fit for our data D. Yeah, that's the learning problem. At least at the high, kind of somewhat vague level. This makes sense, right? That's what we want to do. Yeah? Okay. But to be more precise, what do we mean by best fit? Yeah? Okay. Yes? Yes. Yes, that's right. Not the cluster occurring, but rather when I generate the point, which bump do I pick? That's the probability I pick that bump instead of another bump. Not the bump occurring. There's no such a thing. The bump are already there. We have the bump, right? We have to generate a point using these bumps. But then you say, which bump do I use to generate the point? Yeah? You have to decide, right? W is the probability of your decision. That I decide to use bump 1 or I decide to use bump 2. Yeah? No, not uniform. You have to decide what is the probability. We have to learn what is the probability here. The W is part of the parameters that we have to optimize. Okay. Everyone okay with this model so far? I know we are a bit tired and stressed, so I want to slow down a bit and make sure everyone is on the same page. Since next week we also only have one lecture, right? So there will be some discontinuity. Make sure that everyone is okay now so that we don't forget things by the time we come back from the midterm. Everyone doing okay? Yeah. So we want to. The GMM is decided by this big omega, this set of parameters, and we want to find the best parameters to fit the data that we observe. Now, how do we define the best fit? Yeah. What do we mean by best fit? What does it mean? What do you think would be a good way to define best fit of the data that we have? We have already seen this before, in fact, in logistic regression. Okay. That's a hint. How do we define the best fit to a data that we have? What did we do in logistic regression? So another way to put this, we try to optimize this parameter, right? So we have different choices of big omega, right? One big omega will give us some probability of something. Another omega will give us something else, the big omega. Okay? How do we know which one is better than the other? When we have two different sets of parameters, how do we know one set is better than the other? Given our current data points, right? Given our D. Okay? What do you think? Exactly, yeah. We want to maximize the likelihood that the data that we are given is actually can be generated. Yeah? So we want to maximize the likelihood of observing this data set D. Okay? So we want to pick the omega that is most likely to give us that D. Yeah? That gives us the highest likelihood to generate D, which seems to be a reasonable way to describe what is the best thing, right? What is the best omega. Yeah? So best fit here means the maximum likelihood to observe the data that we have. And based on our data generation model in our hypothesis, what is this probability of observing D? So we denote it in this way. Yeah? It is the probability as a function of the parameter that we have, omega, right? And then this is observing D. Yeah? The likelihood of seeing this whole D. Now, since each data point is generated independently, yeah, the probability of seeing these endpoints will be the same as the product of the probability of seeing each point, right? So this is xn, like that. Right? The probability of seeing each point, the likelihood, this is actually the density. The likelihood of seeing each point. Multiply all together, that's just the likelihood of seeing the entire set of data, yeah? Because these data points, they're independent. Yeah? You just multiply the probabilities. So this is, again, this is because of independent data points. Yeah? So therefore, our objective is to find the optimal omega to maximize this likelihood. Yeah? Maximize this p hat. That means that our error measure, just like before, can be the log loss function, right? Because remember we discussed before, the log loss basically just gives you maximum likelihood. Yeah? So E in, our in sample error, of course is a function of the parameters, big omega. We're going to define it as the negative log of that probability. Yeah? Right? So maximizing p hat is the same as minimizing this negative log, yeah? Because the log is a monotonic function, and then the negative just flips it around. So instead of maximizing, you minimize. Just to fit our canonical form of minimizing the learning error. Yeah? This is in-sample learning error, E in, that we want to minimize. Okay? So, and well, just plug in the per sample error. Then we have this log of the product equals sum of the logs. J goes from, not J, n goes from 1 to n, and then log of p of xn, right? And by our hypothesis, this is simply a log of the sum. This probability, remember, that's we already have a formula, right? How we generate. This is the PDF, right? That's the PDF of the x, yeah, by our GMM model. So we just plug that in. This weighted sum of the Gaussian PDFs. So this is j equals to 1 to k, wj, and then xl now, yeah, uj, sigma j, like this. Okay. And because this naturally is a sum over the sample points, right? So we can naturally define this En of omega, just our per sample error, just like before, yeah? So that this En of omega simply equal to whatever that's inside the sum, yeah? So the negative log of this guy. Xn. Yeah? Only has to do with Xn, right? Does not have anything to do with the other points, because they're independent points, which is very nice. Makes your optimization a bit easier. Yeah, everyone okay so far? This is our error measure. Yeah, That's something that we want to minimize in order to find the best fit for the GMM model. So now the question then is, what is the learning algorithm to minimize this error? Right? That's what the learning algorithm is supposed to do, right? Find the optimization algorithm to minimize the in-sample error. Yeah? So our learning algorithm. Any ideas how we might be able to minimize this guy? Yes? Good, yeah, that could be. Yeah, that's what we use for the k-means, right? But this is not quite the same because we have the Gaussian shape to worry about. Yeah, the distance itself might not be the best thing to minimize. Yeah, it usually does not give you the best solution. Okay, so what else can we do? Oh yeah, that is dependent. But then, as the shape is different, right? As you get closer and closer to the mean value, it gets flatter and flatter, right? It's kind of like your kind of marginal benefit of getting closer is smaller when you are getting very close to the mean value. It gets flat and then a bit steeper and then flat again. You know, it's not a very smooth measurement of goodness, good fit, fitness. Yeah. So we have to do something a bit better than just measuring the distance. Okay. So, any ideas how we can minimize this? We already know something. Yeah. Yes. Gradient descent. Yeah. Well, whenever you don't know how to do, just say gradient descent. That's the best. That's what, yeah, right. It always works. Except in this case, look at how many parameters we have. Okay, with all these different covariances and so on. Even though you could do gradient descent, it's highly complex, and it's really not doable in reality. Okay, even though gradient descent generally works, but it's way too complex. Okay, but that's a good thought, you know. SGD, anytime that you don't know what to do, just throw SGD at it, yeah, and it gives you some answer anyways. But the problem is this, yeah, again, this guy is very complicated. So we don't have a closed form solution for its, we don't have an easy closed form solution for its gradient, yeah, with respect to this big omega. A lot of things there, very complex. Yeah. Even worse, there's another thing that makes it also more complicated. Unlike the logistic regression, when you just take the gradient, you just keep going down. Here we have a constraint. Remember, we have to the W is part of the big omega, right? W is a probability distribution, has to sum to 1. So there's a constraint there. So now you're talking about constrained gradient descent. Okay? What's so difficult about having constraint for gradient descent? What's so bad about having constraint? You do gradient descent, so what is a constraint? You might jump outside of your feasible set, right? Yeah. Previously, in logistic regression, the entire universe is your space that you can go, anywhere you can go. Yeah? But here, it's constrained to the sum of Wi has to be equal to 1. There's a certain set of, only a part of this, the subset of the space you are allowed. What if your gradient descent goes out of this the allowed space? What do? There isn't an obvious way to what you do at a time, right? You go to infeasible state. Well, there are ways. It's called projected gradient descent, that you run a projection back to the constraint set. Usually it still works, okay? But then the projection step is very computationally intensive. So that's another thing that's bad about using gradient descent in this case. We have a constraint optimization problem. Because we have to have the sum over I is equal to Wj, yeah, or equal to 1. Yeah. Here, this is the sum, right? And this is not our covariance matrix. It's just the sum over J. Yeah. So therefore, in general, we do not optimize GMMs using HGD. Okay, so we have to have a new method to do it. Yeah, and we're going to use what's called the expectation. Well, I say this one is the question mark. Yeah, estimation maximization method. Yeah, it's a very powerful method that shows up in many places, and we're going to discuss that when we come back next week. Okay. You already seen it. The k-means algorithm is one kind of EM algorithm. Okay? It's one kind. So here, this one, of course, will be more complicated because of dealing with GML. Okay? So I'll see you next week. Yeah. Meanwhile, everyone take care and do well in your exam. Yeah. I hope. So, but don't stress out too much. Yeah?
On the Gaussian